Velázquez and I'm an international business student. In this video I'm going to teach you through, a key topic from my survey calculus class about the different types of continuity and discontinuity in a function, and understanding discontinuities is super important, especially when analyzing graphs and predicting behavior in economic business models. Okay, so let's start with the basics. A discontinuity is a point where a function is not continuous. In other words, the graph is broken or not smooth at that point. There are three main points of discontinuities. One is removable. The second one is jump. And three is infinity. I'll explain one with a simple example, and another example that is more complex, and I'll show you the graph so you can visualize it better. Well, the removable discontinuity happens when there's a hole in the graph. Let's see that there's a graph here, and this is a continuity, and we have a hole here. That's a removable. So we will have this example that it's fx equals x squared minus 1, x minus 1. I want to clarify that this one is the simple example. Okay, now we have this function, and what are we going to do? We're going to factorize it. How we do that? We have fx. We can see that we have x squared here, so we change signs and we open a new numerator. That is basically x, we open parentheses, x minus 1. Here's where we change the sign, that is sum 1. Divided by the denominator, that is x minus 1. We basically cancel this and we have x plus 1. No? So, as we can see here, there's a hole at 1, and that's a removable discontinuity. We could fix it by defining the value at the point as 2, and the function will be continuous. So, I corten it. So now I'm gonna make the graph of the exercise we just did. We're gonna have something like this, and we know that the discontinuity is gonna be at the point 1. So we're gonna have here 0, 0.5, and 1, okay? So when we do this, the graph shows us that discontinuity is at this point, that is 1, so the discontinuity is the hole that we have at 1. And basically that's the removal discontinuity of the exercise we just did, okay? Ya con eso. Well, hello, I'm here in the elaborate example, and we're gonna use this function that it's f to the x. We open a key and sin x divided by x, and 2 that we're gonna use it if x equals 0, the first one, and 2 if x equals 0, okay? Basically, for all values of x except 0, we use the first formula, that is sin to the x divided by x. But when x is 0, the function is defined in 2. Now here's the interesting part. The limit of sin x to the x approaches 0 is gonna be 1. And this means that the function is trying to be 1 at that point. It's approaching 1 from both sides, from limit from right and limit, no, left, sorry, from left and right. Now, what's the problem here? that the function value at x equals 0 is 2, not 1. There's a mismatch between what the function is doing around 0 and what's actually defined to be at 0. And this creates a removable discontinuity. It's called removable because we could literally fix the function by refining it at one point. If we simply set f0 equals 1, the function would be continuous. Okay, now we can go to the graph part that I already prepared. So we can see that the curve is smooth and it approaches to the value of 1 as we move toward 0 from the left and the right, no? But instead of being 1 at x equals 0, there's a red dot at 2, that it's this one, that it's from here. This shows a hole where the function should be and a dot where it's defined. You can also see dash horizontal line at y equals 1, that is where the removable discontinuity. There's no jump and no vertical asymptotes, just a missing or wrong point. And why it matters? This type of discontinuity is very common in business or science when something is almost smooth, but has a small exception or an error in data entry or modeling. In real-world applications, you might remove this kind of discontinuity during optimization, modeling, or simplification. That's why it's called removable. It also helps to practice identifying linear rational or trigonometric functions like this one. So basically to conclude this, a removable discontinuity happens when the limit exceeds, but the function value doesn't match. In our example, sin to the x divided by x is smooth, but the definition at x equals 0 breaks the smoothness. And basically, it's gonna be all. Thank you. I'll see you later.
So to end, this is my personal opinion about learning with AI, and I want to quickly reflect on this learning activity. And first, yes, we can absolutely use this method for other calculus topics, whether it's optimization, limits, or integrals. Creating example graphs and short video explanations helps make abstract concepts clear and relatable, especially for business students like me. And in the second part, I will also that the role of the professor is evolving, and with AI topics and tools that we can generate step-by-step solutions or visuals instantly, professors or the professor now can guide us to think critically, explain our reasoning, and apply concepts creatively. Instead of just teaching content, they teach us how to use tools effectively and communicate like real-world problem solvers. And basically, that's my personal opinion about learning with AI. I think it's a good option for us, the students, because now it's basically the world is moving with AI, so it's important they teach us how to use AI to our convenience and our power. So that's all. Thanks for watching my video, and that's it.